Good morning. Here we are at the physics video lecture. Physics 105A video lecture 37. Getting towards the end of the semester. We're talking about systems of many particles now. So this is a great topic. And let me write down a bit of what we had last time and we'll keep going. So the idea was we have many particles, M1 through Mn. I'll draw 3 of them. I'll draw 4. They have their position vectors, etc. And each particle is subject to Newton's law. So we have, for the ith particle, m sub I times the acceleration is equal to f sub I, and I'll go to the point we had discussed before. We can break up the force, right? It could just be f sub I and not mention the external, but we can break up the force into external and internal forces. So this would be f sub I j. J is going to go from 1 to n, and j is not equal to I. Okay, so those are all the forces of all the other particles acting on the ith particle, say m sub 2. External force, and so these would be the forces of interaction, the particles amongst themselves. The external force could be a uniform or another, doesn't have to be a uniform field, but a field to which they're all subject to. For example, you could have the Earth, Moon, and the Sun, or maybe even the entire solar system. But if we just had the Earth, the Moon, and the Sun, then we could say, well, the Earth and the Moon are interacting between themselves, but the external force for both of them could be the gravitational field of the Sun. And then we just have the Sun out there, imagine in some fixed place, right? Whereas Earth and Moon would be moving. Okay, so what we're going to do next, and that's what we had on our list, was the idea of a potential energy. Okay, we're going to go straight to a potential energy. For this system, we're not interested in explicit time dependence and what have you. So we're looking for forces as a function of position. And that would be a function of all of the positions, r sub 1 to r sub n. So in this general expression, now we're talking about both of these. We're not differentiating between the two types. So if we have a force like that, and if f sub I can be obtained as minus the gradient of a potential energy function, R1 to Rn. So if this is possible, and of course we know there are things we have to stipulate about the potential energy in order for it to be a legitimate example. On the other hand, we know that the gravitational attraction between two particles has a potential energy, and if there's a whole set of them, it's just more of the same. Okay. So that's the situation. If we can express the force as a function of positions, and if the force can be expressed as the gradient of this potential energy function, then what we'll find is T plus U equals E equals constant. So it all comes down to being able to express the force in this manner. and then we will have conservation of energy again. So I'm going to show that first. In fact, I'm going to show the proof of this first, and then we'll go back and look at some examples of what we're actually talking about. Okay, good. And oh, by the way, the gradient here, I actually have to put a little subscript, because what this means is I'm taking those three derivatives with respect to the ith position here. Okay, so that was important. R sub 1 to R sub n with respect to the ith position vector. Good, but let's go ahead and prove this first. Energy conservation. So proof is T plus U is going to be the kinetic energy of the entire system of particles. So that will be the sum of 1/2 m r sub I dot squared, I equals 1 to n, plus u of r1 to r sub n. And to prove that this is constant, we have to take the complete time derivative and show that it vanishes. So ddt of kinetic plus potential energy equals, well, right here we have a sum, 1/2 m, and then the time derivative of this r sub I dot squared is 2 r sub I dotted into r sub I second derivative, I equals 1 to n. And I'll go ahead and do the little calculation for this right away. Of course, we're going to see the, oops, not the n, the 2 cancels. I'll go ahead and do this little calculation right away. Important for you guys to know. So you've got your R so first of all, the square of a vector is the vector dotted into itself, dot product with itself. So this is, we may have done this before, but it's all right. So this would be x dot squared plus y dot squared plus z dot squared. X dot, y dot, z dot are the components of this position, velocity vector. Dot product with itself. That's fine. So then you can see you're going to get 2x dot x second derivative, y second derivative, 2z dot z second derivative. So you can pull the 2 out, and now you can see that we have, those are our velocity components right here, dotted into the acceleration components. So yes, that's r dot r second derivative. Okay, so that's good. Now here we have to take the so we just took the complete time derivative of the kinetic energy. Here we have to take the complete time derivative of the potential energy, and there we need the chain rule for multivariable functions. I'll write it out just in the short symbolic form. Namely, what you're doing is you're taking you're taking derivatives. Let me write it down and then I'll explain it. So what we're going to have here is du dr sub I. And what I mean by this is exactly this here. It's another way of writing it. So if I say that partial with respect to this vector, I mean those three derivatives that make up that gradient. Okay, r sub I of the argument, I'll just write r. And then dr sub I dt, okay, summed up I equals 1 to n. Now this is a velocity vector. Okay. So this is what I have. I equals 1 to n. I have a common velocity, the r dot. Oh, by the way, this is a dot product. I have r sub I velocity, open parentheses, m r second derivative plus du dr. But this is what we're saying has to hold true. So this gradient is equal to minus that force. So this is just Newton's law for each individual particle and equals 0. So the whole thing equals 0. So let's talk a bit about what I just did here with the chain rule. Okay. Okay, so here's a note on the chain rule. For functions of many variables. Suppose we have, we'll start with one variable. So suppose we have u of x of t, right? And then the time derivative is u prime of x dx dt. That's the chain rule for a function of one variable. For a function of many variables, so now if we take the time derivative, of course it wouldn't have to be time, but since we're talking about time derivatives, I'll just do it this way. Suppose we had u of x1, x2, x3, all the way to x sub 3n, and they're all functions of time. X of I is equal to x of I of t. Then it's just going to be the sum over I equals 1 to 3n. Yeah, why am I doing 3n? I'm not generally going to do that, but the idea here is that each of these three, 1, 2, and 3, that belongs to r sub 1 and so forth, okay? We're always just going to use n, but for now, we'll do this. So yeah, what do we have? We have partial u, partial x of I. I'll just write of all the coordinates. And then dx of I dt. So yeah, it's exactly the same as this rule, except you do an entire summation, okay, over all the variables. And the deeper reason for this, someday I'll set up a lecture just on the chain rule multivariable calculus. The deeper reason is that the derivative is a linear operation, and this is in essence matrix multiplication. In general, when you're doing chain rules, you're doing a matrix multiplication. In this case, it is a multiplication of two vectors. Okay? But that could be a column and a row matrix if you wanted to look at it that way. All right, so linear operations can be expressed in terms of matrices. Be that as it may, what I'm going to do is call this vector of all of these partial derivatives, du dx, x equals 1 to 3n, it's been dotted into the 3n velocity components. Okay. So yeah, oh, this needs a vector as well. So that's what I was doing, except since I have components 3 at a time, namely from each particle has its own 3 components, then I sum over this way. So there should have been a subscript I right here. Good. So we use a lot of chain rule for functions of many variables coming up next semester. So it's a good place to get started. So what do we have? We have conservation of energy. And what that depends on is the existence of a function, we're calling it the potential energy function, that we can get the forces by differentiation, from which we can get the forces by differentiation. Okay, consult the clock, see what's going on here. Okay, so next, I want to give some concrete examples of what we just did. Okay, nice to know we have conservation of energy. Of course, now we have n particles, and this is just one number. So, in a 1 degree of freedom system, energy conservation took you right to the answer, but more than 1 degree of freedom, it's just one quantity out of 3 n's. Okay, so go ahead and set this up. Yeah, so we're going to go back to our example of the 2-particle gravitating system, and then we'll generalize that. So for our example, 2 particles M1 and M2 with their respective vectors, position vectors, and gravity. So now we have U of R1 and R2 is equal to minus G M1, M2 over R1 minus R2. And actually the order doesn't matter in this expression, the minus sign does. Remember, this is just our U of R is equal to minus alpha over R. But instead of just having it with respect to a particular origin, we just have these 2 particles. Okay, so and the distance separating them. So what about the force here? Okay. So if that's the potential energy, how about F sub 1? In fact, let's draw a picture before we keep doing this. So we got plenty of room here. So let's go ahead and have, this is M sub 1, R sub 1, R sub 2, M sub 2. And now we're going to do these forces. So F sub 1, so the force on M sub 1 should be pointing at M sub 2, as we know, right? Gravity is an attractive force, and the force on M sub 2 should be pointing at M sub 1. So we just do our derivatives, we're going to have minus gradient sub 1 of U of R1 and R2. Be careful with our bookkeeping. So we have minus times minus is plus G M1, M2. And now the derivative with respect to R sub 1 here is going to be minus 1 over R1 minus R2 the quantity squared. And then the inner derivative, since it's with respect to R sub 1, is going to be the vector R1 minus R2 divided by its magnitude. We've done this in the general, we've done this in this form here, and actually nothing has changed, okay? Because we're just treating R2 as the origin. So let's make sure we get something useful out of here. So R1 minus R2, as you guys well know, is pointing at R sub 1, right? So this is R1 minus R2. And our force, we have a minus G M1, M2. There's the minus sign right there. R1 minus R2 squared. So that's the 1 over R squared law, just the separation distance squared. And this here is a unit vector. So R1 minus R2 divided by its magnitude. Start running into a bit of bookkeeping here, but the meaning should be really clear. So this is F1, and that minus sign means it is, here I'll put parentheses around here. Minus sign means it's pointing in the opposite direction of this R1 minus R2, so that's fine. So what about F sub 2? Okay, what about the force on the second particle? Everything is going to be the same in our calculation, except when it comes time to do the inner derivative here, since it's going to be with respect to R sub 2 right here, we're going to pull out another minus sign. Okay, inner derivative. So I'll put a note here before I write it down. The inner derivative or chain rule brings out another minus sign right there, and therefore it'll be this expression with, right, it'll be this expression with a plus sign there, which means it's directed in the opposite direction, and so that is equal minus F1. We don't have to do it again, right? It's clear. The chain rule brings out another sign here from that differentiation right there. So that's how it's done. So we may have to spend a little time reminding ourselves of what's going on when I did this derivative here. Basically, I just treated it like 1 over R, so I had the derivative was minus 1 over R squared, which is this magnitude squared, and the inner derivative, yeah, I'll even put a note there. So note, for one particle, which is that example right there, gradient U of R, and I'll write it as a vector R, although it's a function of the magnitude. Gradient U of R is equal to U prime of R times the unit vector. Right. That's when we're going to have to practice, because that's all I've done. I've applied that to this situation here. If I differentiate with respect to R1, I'm treating R2 as the origin. That's all there is to it. No big deal. Yeah. The major practice we may postpone till next semester. Yeah, maybe let's complete this little proof here regardless. I think we've done this before, but it's good to practice, because dx of I of u of r, and in fact, it is important that the potential energy is a function of magnitude. It is here, right? It's not a function of it's a function of that difference there of the magnitude. R is equal to u prime of r, and then dx of I of r. Okay, but dx of I of the square root x1 squared, x2 squared plus x3 squared, right? That's r, x squared plus y squared plus z squared. If I go with respect to the ith one of these, just any one of those, that's a 1/2 root, same thing, in the denominator, and then 2xi. 2's cancel, equals xi over r, the original r. So that equals u prime of r, x of I divided by r. And since that's the ith component, the set of 3 of them is that vector, which is right up here, okay? So that's the proof of this again. We'll be dealing with more of this next semester. Okay, so that was 2 particles. Let's see if we can set up n particles. Now let's write down for a set of n gravitating particles, we want the force on the ith particle. And the way we'll do that is this. We had the force on the first particle. Leave a little room here, okay? First particle was minus g. Well, I'm just going to write it out. You'll see this makes complete sense. Ri minus Rj squared. Ri minus Rj vector, Ri minus Rj. In fact, here's what I could do, since I have an eraser here. We had F1 was equal to minus this. We had R1 minus R2 to R1 minus R2. That's a magnitude squared, right? That's Newton's law. This whole thing is the unit vector. So this will just generalize. we'll just do a big sum and name the one that we're looking for. So the force on the ith particle is going to be the sum of minus g, by the way, this was m1 and m2, minus g mi mj ri minus rj squared. It's just bookkeeping, right? And then times that unit vector ri minus rj divided by its magnitude here, ri minus rj. And since it's the ith particle, we're summing up j equals 1 to n. And of course, we're leaving out j equals I. So j does not equal I. So yeah, there's some bookkeeping, and that would be the force on the ith particle from this whole solar system full of gravitating particles. Here's a question. What would be the potential energy that delivers this force here? What potential energy U of R1 to Rn would give us this force here? Magnitude. Let's see. Long time. Well, that's an interesting question. We'll save that for later. Or you guys could try to tease it out. There are a couple of different ways. It comes down to summing. You know, remember U of R1 and R2. We just had up on the board there. Do we still have it? No. Was just minus g m1 m2 r1 minus r2. So there's a summation over these with I and j. You have to be careful about counting them, up. You know, I'll write down the answer. It's an interesting one. I'll write it down. You guys can see if you can actually do the derivatives. Maybe we'll save that for next semester. So here's the answer. U of R1 to Rn. It's minus 1/2 double sum I and j 1 to n. Got the minus out front, so I've got the g mi mj ri minus rj. It's a tricky differentiation. The thing is, what you do is you do the 1/2 and the double sum, because then your I and j and I, you know, are symmetric, so they show up twice. So R1 minus R2 shows up, and R2 minus R1 shows up. So you add them twice and put a 1/2 in front, and then you say I is not equal to j. And this thing, if you're careful, you take some gradients of this along the lines of what we just did, and then you will obtain this sum right here. Okay, good. So much for that. Equations of motion. Easier to write down than it is to solve them. Okay, what are we going to do next? I think we have time for one conservation law. Yeah. So we already have energy. So we're going to look now at another conservation law. I'll break the suspense. We're going to look at the law of conservation of linear momentum and some consequences of it. So next, linear momentum. do a couple steps to get there. So we're going to return to the set of n particles, so m sub I, r sub I, acceleration is equal to f sub I external plus the sum of all these fij, j equals 1 to n forces. Okay, so we've got the external forces, the internal forces, n particles, j is not equal to I. Now, that's true, right? I equals 1 to n. We have n particle system. And if this is an equation, then we're just going to add all these up. And so next, we're going to do sum over all of these m sub I, r sub I second derivative. I equals 1 to n is equal to the sum of the external forces plus this double sum. So now it's I 1 to n, j 1 to n, I not equal to j. So now we have a double sum here of the fij's. And these are internal forces, and we have a really simple argument. Newton's third law says that Fij equals minus Fji. Okay. That's by Newton's third law. Because they're just equal in magnitude, oppositely directed. Those are the interaction forces between the ith and the jth particle. So by Newton's third law. So this goes away, this vanishes, because they sum up, Fi, I'll just put it here explicitly, Fij plus Fji in that double sum equals 0. So the internal forces all sum up to 0, and we're left with this equation here. This can go. So what we can do is just write, regarding what's under here, we can pull one time derivative out, sum of m sub I, r sub I dot, is equal to what we're going to call the net external force. Okay. So I'm actually defining these terms, so right underneath here, that's what I mean. And this is the linear momentum, or d dt sum over p sub I. So these are individual linear momenta, mv, or d dt of the total linear momentum, I'll use a capital P, is equal to this net external force. So yeah, if the net external force is 0, then the total linear momentum is conserved. If F net external equals 0, then P equal to the sum of all of these individual momentas constant, so that's conservation of linear momentum. For example, when we had our two-body problem, so recall two bodies. Remember we had m sub 1, m sub 2, and I put a little star there and said that, you know, we were taking the origin as the center of mass. So remember, two bodies where center of mass was the origin. That's because the center of mass is moving with constant uniform, with, you know, constant velocity, and we just take that as the origin. Because this two-body problem only had these two internal forces, so it had no net external force, therefore it had conservation of linear momentum. Good, that's a good place to have ended here for the day. Was the origin. There were no external forces. Remember, it was a two-body problem. Therefore, we had M1 R1 dot plus M2 R2 dot that's an R, was equal to 0. And we were able to then choose M1 R1 plus M2 R2 is equal to a constant. And that was the uniform motion of the center of mass. Good, so yeah, like I said, the two-body problem actually always allows us to have illustrations of these more abstract theorems. But it's a good place to stop. We've got the conservation of linear momentum. You can have a whole cloud of any number of particles interacting with each other, but in the absence of an external force, their total linear momentum will move uniformly. And what we'll do next time is talk about the center of mass, because I just brought it up. So we'll even put this here in on our notes. Next, center of mass. And we'll call it a day and see you guys next time.